explain us about diversity-aware routing.
Thank you. So hello, I'm Julius Krobacek. I'm in Paris, and I'm very pleased to be giving this talk here at WBM version 4. And I'd like to tell you a little bit about routing, taking into account radio diversity, taking into account different radio frequencies. And this is some work that I'm doing within the routing protocol Babel. So Babel is the minority protocol here. We all know OLSR, which is the historical link state routing protocol for mesh networks. We all know about Batman, which is a somewhat using original technique, somewhat similar to distance vector, and the young up-and-coming routing protocol for mesh networks. Now, Babel is a more experimental protocol. It's based on the ideas of distance vector. It's a pure distance vector protocol with a number of techniques used to make these classical techniques usable in mesh networks. There's one property which I'm very careful to preserve. It's an extremely malleable protocol. It's a protocol in which is very modular, in which you can change various things, and in particular, you can change the metrics and the route selection. And I just, before I go on, like to have everyone notice the nice brand new Babel logo, which has been designed today. This is the first time you're seeing it. So the logo is due to Boris, who is over there. And the font that he used is called Courier by Małgorzata Budyta, and that was a student project in 1963. So I all wish, I see that there are a few students here, I all wish you that your student projects will be used 40 years later, 50 years later, for something you didn't expect. Okay, mesh networks. So I have a mesh network. I'm not going to explain to you what mesh networks are. You all know what mesh networks are. But they have one property, which is that in mesh networks you are going to have multiple radio links, multiple radio nodes in a single geographic area. So this is a map of the center of the world, if I understand things well, a place in which converge most of the internet backbones in Catalonia. And in such a place, you are going to have those multiple radio links. And of course, we are speaking of radio. In radio, if you're listening, if you're speaking, you cannot listen. And the various radio channels are going to interfere. Now, there are two kinds of interference which you need to distinguish because the techniques that you are going to use to solve them are going to be different. There is interflow interference and intraflow interference. Interference between different routes and interference of a single route interfering with itself. So an example of interflow interference, you have a guy over there who is communicating with two guys called A and B. And those two guys send data to the guy up there. And if they try to send the data at the same time, then neither of the two pieces of data are going to arrive. And in the case of intraflow interference, there is A here who wants to communicate with C. He starts sending data to B, and while B is retransmitting A's packet to C, A cannot speak to B. Now, I'm going to tell you about what I'm doing within BabelZ, which is an experimental branch of Babel that deals with intraflow interference only. So only this kind of interference. Interflow interference is something that I'm leaving for later. Now, the symptoms of intraflow interference are very simple. Throughput decreases with the number of hops. So in the first case, you have just one hop, and you're getting performance that is 100% of what the link is supposed to be giving you. Okay, it's not going to be 100%, but it's close enough. Now, you add a hop in the middle. In this case, A is speaking to B, and while B is retransmitting the packet to C, A cannot speak. So the throughput is divided by 2. If you add another hop, you would expect it to be divided by 3. A speaks to B, while B is resending the packet to C, A cannot speak. C is resending the packet to D, But we all know that interference areas are much larger than the communication radius. So typically A cannot speak while C is speaking. Now you would expect the 3 links to divide the airtime into 3, but that's not what happens, because A and C are not synchronized. And you end up having just 1/4 of the expected throughput. And it goes on exponentially up to more or less 7 hops. At 7 hops, it becomes constant. But you've divided 7 times, and you have less than 10% of the link throughput, of the link capacity. So how can we minimize this interference? Well, one thing is we can use hybrid networks. I think that we're all doing that. We're using networks in which we have wireless links, and when we can, we put cables, we put fibers. The cables and the fibers do not interfere with the radio, so we're minimizing the interference. Another technique is to put artificial obstacles, to put your antennas in places where they are protected from part of the network in order to minimize interference. The most effective technique is to use directional antennas. With directional antennas, you're interfering in one direction only, and you're going to minimize interference. The problem being, of course, that you cover a smaller area, and the other problem is that directional antennas are very difficult to set up. You need to aim them precisely, and that complicates everything. And finally, an idea that has been around for a while is to put different nodes on different radio frequencies and to avoid interference by having different nodes on different non-interfering frequencies. So I'm coming back to my examples before. So interflow interference. I'm not going to speak much about interflow interference in this talk, but just an example. In the example before, if you assume that everyone has 2 radios, then A and B can choose different frequencies to communicate with the truck at the top. So that's the easy choice. A will choose one frequency. If B is able to detect that there is traffic on the first frequency, it might be able to switch to the other frequency. A more difficult case is this one, in which A might start to speak first and use the solid frequency, and B is stuck. So here we would like A to be able to decide, well, I'm going to use the dashed frequency because it is less crowded. Now for intraflow frequency, it's a little bit different. So up there it's the easy case. A wants to speak to C, and B has chosen one of the frequencies, say the solid one. Then A, if it is able to detect that B is speaking on the solid frequency, will be able to choose the dashed frequency. And the difficult case is this one, in which B has chosen the dashed frequency to speak to C. And so, if B has chosen the dashed frequency to speak to C, everything goes well. On the other hand, if it chooses the solid frequency, then A is stuck. There is no way it can force B to switch to the dashed frequency, except if there's some form of explicit signaling. Now, I'm doing that in Babel, and Babel was very carefully designed to allow flexible metrics and flexible route selection. So Babel was designed after I had looked very carefully at OLSR, decided that what they have done in OLSR is very smart, but that they are having problems with not being able to experiment with different policies, because OLSR tends to be somewhat rigid. If you've chosen to use a given metric, then you need to have all your network using the same metric. So in Babel, I went out of my way, knowing that I would probably get the metrics wrong at least for a few years, to design it in such a way that I can easily switch the metrics and the route selection policies. It goes so far that in the document describing Babel, RFC 6126, there aren't any metrics defined. It says, take a metric, and the metric should have such properties, and all the rest will work. It might not do anything reasonable if your metric is not reasonable, but the algorithms are going to work. So it's not that bad. There is an appendix in the document that says, look, we've tried those metrics and they work, more or less. Okay? If you have any better ideas, we're interested. Now, BabelZ, with the Z being in honor of Zubab, who explained those things, the interference things, for the first time to me, sends explicit channel information in root updates, which allows it to avoid, to a certain extent, if there are enough radio channels, intra interference, and doesn't do anything about inter interference. A little bit of terminology so we can communicate. A link is a single hop. Think an Ethernet cable. That's a link. Okay, we're speaking radio, so they are not Ethernet cables, but they are still links. They are just like links, except that there's no cable. And the root is a sequence of links. So when we are speaking, take this root, we are speaking of the sequence of links that are being taken. And concatenation of roots and links is written using a dot. So this root, using the links L1, L2, L3, is written L1.L2.L3. Now, our goal is to take the best path in the network. Now, the best path is often obvious intuitively, but we need to quantify it in order to build it into our algorithms. So we define two kinds of values, costs, and every link has a cost. So the idea being that the cost is what you want to avoid. If you have a link that has high latency, that has low throughput, that has something undesirable, you give it a high cost. Now, the metric is intuitively the sum of all the costs of the links in a route. So links have costs, routes have metrics. And there are two operations on costs and metrics. There's addition. Now, I write it with a rounded plus to make it clear that it's not necessarily the addition that you learned about in nursery school. It's some operation that behaves more or less like addition. And there is an ordering, which I write with a squiggly inferior sign, which allows you to compare roots. So the ordering, the intuition of the ordering is that smaller means better, means cheaper. Now, if I have a root, I can add a link at the beginning. And the metric of the longer route with the link put at the beginning is computed by using this addition operation. And the metrics are compared using this squiggly thing. Our goal, the goal of the routing protocol, is going to be to compute the set of routes that have the smallest according to this ordering metrics. Okay, so I'm not making any claims here that this is actually what you want in practice. What I'm claiming is this is my definition of what the routing protocol is doing. Okay, a few examples of metrics. So shortest hop routing. Henning is here. So worst first routing. You want to minimize the number of links that you're going to follow. So you give to each link the same cost, some constant. Let's check some non-zero constant. Let's pick 1. Addition is just addition. It's plus. And the ordering is just the ordering on the integers. Okay, you all know that. ETX. In ETX, as used by OLSR in the ETX variant, the cost is some fairly reasonable and rather convincing formula that depends on packet loss. It's of no concern to us. It's something that increases when packet loss increases. These are numbers, and so addition is just addition, the usual addition of numbers. And the ordering is just the ordering on integers. Smaller is better. Okay, hybrid routing. This is what we do in Babel, in the actual implementation of Babel as opposed to the specification, where we don't define a metric. So on wired links, we use shortest hop. The idea is that following just one Ethernet is better than following 2 Ethernets. And there is not much more you can do except if you want to react to traffic patterns, which is more difficult. And on wireless links, we use ETX. Now, those things are multiplied by some constants that I've chosen by looking at the network and thinking, oh, well, 64 looks good to me. And they are added. So there's nothing really new here, except that we're combining two additive metrics. And here's an example of a metric, which I'm just putting here to show you that those things are not necessarily what you're used to. Suppose that you want to maximize throughput. You want to take the thick tubes. You're willing to take a bad latency hit. You don't care about packet loss, but you want to take the fat tubes. Then the cost is going to be the throughput. Now suppose you put two tubes, one behind the other. The throughput that you get is the smallest of the two. So the addition operation, rather counterintuitively, is the minimum operation. And now you want to maximize throughput. So larger is better. And so the ordering on the metrics is the ordering on numbers, but inverted. Okay, so that's an example of a non-additive algebra for metrics. Okay, so I'm saying if you use Babel, you can choose your metric. And you're obviously going to tell me it's not going to work if I choose any random operation. It must have some properties. Well, there are two properties that we need. And the first one is strict monotonicity. I've written monotonicity here. So strict is not equal in addition to that. Now, I have a root that has a metric m. I add a link with cost c in front of it. Then I get something that is less good. That's quite intuitive. If you have a longer root, you want it to be worse than the suffix of the root. Without that, everything collapses. You are not going to achieve much if you're not monotonic. And the other property, which is less intuitive, is isotonicity. It's another monotonicity property, but we use a different name. And I'm going to come back to isotonicity. I'm going to explain it later. So just to tell you, if we're not isotonic, the network doesn't collapse. It just behaves in funny ways. And I'm going to describe it later. Okay, so the basic idea of diversity routing is that you don't want to interfere. You don't want to interfere, and because of that, you want to be using as many different frequencies as possible. You want to maximize the diversity of your routes. Now in BabelZ, we're using three approaches for that, which I'm going to describe. One is that we avoid hopping on the same interface. You have your router, a packet is coming back on an interface, you have two interfaces. Well, if it's possible, try to push it out through a different interface. With luck, it's going to be on a different frequency. So that's the simplest diversity strategy you can have. I think somebody mentioned it about Batman earlier doing that. That's a very old idea. It's been used quite a lot. It works surprisingly well. And that is what you get with BabelZ if you call it with the flag -z with the parameter 1. Now, you can do a little bit better than that without paying too much, which is by taking into account not only that they are distinct interfaces, but that they are actually using different radio frequencies. That's what we do with -z2. And all of those things are local. They only consider the coming packet and where you push it back out through. And in some cases, we would like to have more memory, and that's what happens in BabelZ if you call it with the option -z3. I'm going to describe those in detail. So first idea, choose a different interface. Now you can do that in the route selection procedure. You can hardwire it in your routing protocol, and it's, I think, mostly a choice of taste, whether you want to hardwire things in the algorithms or whether you prefer to encode them in the metric. I'm finding it easier to work with the metrics. So one way you can do it is that if you're hopping over a single interface, if you're pushing the outgoing packet over the same interface, you're going to assign a metric that is the addition, just as in the plain basic ETX or shortest hop routing algorithm. On the other hand, if you're going through a different interface, which is something you want to encourage, you want to use a smaller metric. So instead of adding C, the cost of the outgoing link, you add 1/2 of C for the right value of 1/2, which might not be exactly 1/2. I'm starting to think that the right value of 1/2 is 1/3, but that is just experimental. We need to find it. Okay. Now a slight improvement over there, which is to prefer a channel that doesn't interfere with the last hop. So the formulae are the same. You're still using this 1/2 of C, but the condition is a little bit different. You're not using the full formula when it's the same interface, but when it is an interface that interferes with the incoming interface. So you need the right definition of the interference, and interferes means either they are the same interface, every interface interferes with itself, or else they are distinct interfaces, both are radio interfaces, and they are tuned on the same channel. Okay? Now that gives you a slight improvement, because it deals with the case in which you have put multiple radios at the same frequency in a node, which is okay, but not really interesting. But there is a very, very nice side effect, is that suddenly you no longer need to hardwire into the routing algorithm a preference for wired interfaces, because wired interfaces interfere with nobody except themselves. And so in general, the algorithm is going to automatically prefer the wired interfaces as much as possible. And that I think is a very nice property. The flaw, of course, is that you need to write a lot of non-portable code in order to work out what the frequency is today. So you have an interface, you need to work out what the frequency is. It works in a certain way in Linux 2.6, except on Android devices, in which there is some sort of weird bug. I don't know if we've implemented that for BSD yet.
It's not implemented yet.
Okay, so you end up having the usual problems with non-portable code that you're doing. That's the only problem with that. Okay, and the third non-interference algorithm is non-interference with memory, in which the formulas are again the same, but the side condition is different. Instead of saying the incoming interface and the outgoing interface interfere, you say the outgoing interface, L, interferes with some hop that was taken by the packet earlier on.
Why not backwards? Why not forwards?
Because you're pushing a packet out.
Why don't I try to avoid interfering with...
Sorry, it's going forward. Of course, it's going forward. I'm speaking of propagation of the root. So the interface, the root over which you're going to push it, takes a hop that interferes with the incoming interface. I'm saying it the other way around. You're right. So I have this packet that came, and I'm looking whether it interferes. And otherwise, you use the smaller formula. And the trouble with that is that you need to change the on-the-wire protocol. -Z1 and -Z2 use the normal on-the-wire protocol because all the decisions are local. You look at the incoming, outgoing interfaces, and that's all. Here, you need to have all the information about the hops in your root. So root announcements need to carry the sequence of channels. And, sorry, that was on the next slide. So you need to know about the full set of channels taken by a root, and so you need to encode it somewhere in the protocol. So we're encoding it by adding an extra sub-TLV within the update TLVs used by Babel. And this is designed in such a manner that standard Babel nodes that don't speak Z are going to ignore this extra data. They're going to see the updates, they will see some garbage they don't understand in the update, they're just going to ignore it. They will never attempt to parse it. And so you can have a network that uses both, although you're actually changing the protocol. Okay. So earlier I was telling you that metrics need to have two properties, which are monotonicity, which is quite intuitive, and the other one is isotonicity. So the definition of isotonicity is that if I have two roots that have metrics m and m prime, call them r and r prime, and r is a better root than r prime. So m is smaller for this weird ordering than m prime. And you prepend a link to both roots, the same link to both roots. Then you're going to preserve the ordering. So basically what it says is that if B makes an egoistic choice, then this choice is going to also be good for A. You're prepending a link to the root taken by B, and what is best for B is also best for A. So the slogan I'm proposing for isotonicity is the property that says that liberal economics works. So if you believe that the universe is isotonic, then liberal economics works. Now, once you take into account diversity, then your metrics almost automatically become non-isotonic. So here's an example. B and C are double radio nodes. So think that they have one link, the solid line, which is at 2.4 gigs, and they have an extra 802.11a radio, which is this one. Now we all know that at 5 gigahertz signals don't propagate as well as at 2.4. And so the dashed link has a metric that's a little bit larger than the solid link. There is a little bit more packet loss, say 1.2 instead of 1 as the resultant cost. Now A is your laptop, and because you're a cheap person, you bought a laptop with a radio that doesn't speak 5 gigahertz. And so in order to communicate with B, you're going to have to use the 2.4 radio. Now B is making an egoistic choice. It's choosing to take the solid frequency. And A would prefer B to take the dashed frequency. So you end up with B's egoistic choice not being optimal for A. And if you write it down with the metrics, you're saying that this one, the metric of the solid line, is smaller, better than the metric of the dashed line. But on the other hand, when you prepend the dashed line to both of them, then the metric of solid dashed is, did I invert it? Yes, I inverted it twice. So that's the other way around, excuse me. The metric of solid dashed should be smaller than the metric of solid solid. For A, it is preferable to change frequencies, and you violated the isotonicity property. So, what does that mean for the protocol? Here's a 10,000 meter view of what Babel does. It is a big loop on every node, and it selects a route, and then in an infinite loop, whenever it sees a better route, it switches to the better route. Okay, I think that's more or less what most distance vector protocols do. Now, strict monotonicity tells us that this process is going to converge. Strict monotonicity says that you cannot infinitely find ever better routes and keep going. And when you converge, you can no longer find a better route. So every node in the network has found the best route. It cannot switch to a better one. And so what you have is a local optimum. Nobody can improve his own situation by switching to a different route. And what isotonicity says is that this local optimum is actually a global optimum. Is that by everyone making egoistic choices, you've ended up with the best possible situation for everyone. And this property is no longer going to be true in the case when isotonicity is violated. So coming back to the previous example, there's supposed to be a figure up there. The same figure as in the previous one, so I hope you still have it in your hand. B selects the solid link on the right. A would like B to select the dashed link. And this is not optimal. Although everyone has made the optimal choice for himself, we haven't reached a global optimum. So we have a local optimum that is not a global optimum in this case. Proper solution. Let's change the structure of our routing tables and use multiple routing tables, one per incoming interface. So allow B to route differently its own packets and packets coming from A. And the trouble with that is that it's difficult to implement, even if you use only one operating system. If you do it only for 2.6 Linux, you're still going to have a lot of trouble with it. And as far as I know, nobody has implemented it yet. Am I wrong, Henning? Is that okay?
I have to read some papers that say they have implemented this, but I'm not.
But you don't have any evidence either. Okay, that's the impression I was having. Now, so we have a problem. There is the right solution, and the right solution is difficult, and we're too lazy. So there's the other solution, the wrong solution, which is let's ignore the problem. Let's say, okay, it's going to be a local-only optimum. There will be some networks, some pathological networks. So instead of saying we're lazy, I say you're being pathological. So you have some pathological networks in which BabelZ will converge to a local-only optimum which will not be global. We'll deal with it. That's the way BabelZ works. Okay? So, to conclude this, so the first version of this slide was saying that BabelZ is ready to be merged. And then yesterday at 3 a.m. it crashed. I fixed the crash. I've added the word almost over there. It interoperates with RFC 6126 Babel. So if you put a network in which some nodes are using standard Babel, some nodes are using the Z variant, the network is going to work with the BabelZ nodes, with the Babel nodes ignoring the BabelZ extra information, and the BabelZ nodes realizing that those dumb Babel nodes are sending them incomplete information, and they will try to guess. So the guess is worth what it is worth, but basically the guess is if I see a small network, I assume it's just a small metric, I assume it's a single link. Otherwise, I assume it's a link that interferes with everyone, and the effect will be that the BabelZ node will tend to avoid the Babel nodes if there is any other choice. It has been shown to work in limited tests, as in you put 6 single radio routers connected by cables in pairs at different frequencies, and it does the right thing. And tomorrow is going to be the first medium-scale test of BabelZ. That is, we are going to use BabelZ nodes in the battle mesh. And so they will probably crash. I'm a little bit less optimistic since last night, but we'll see how it goes. And what needs to be done? Well, fine-tuning. In particular, I don't know what the right value of 1/2 is, and I think it's smaller than 1/2. I'd like to do some theoretical work. I'd like to understand which are the networks in which you cannot have a failure of isotonicity. So I was saying earlier on, I claim that networks in which you can find contradictions to isotonicity are pathological. Well, that's very nice, but I'm only allowed to make this sort of claim if I can tell you, look, if you do that, then you are not going to have any convergence problems. And right now I'm finding it difficult. I went through a lot of ups and downs of phases of optimism. Yes, I have a nice theoretical criterion, and then finding counterexamples. And finally, right now I'm not promising, the reason Babel is separate from BabelZ is that I'm not promising I'm not going to change the protocol. And so I need to finalize the protocol, decide, fix the on-the-wire encoding of the diversity data, and of course write it up. Thank you for your attention. Jan?
One comment to isotonicity. Yeah, I've read papers with really nice routing metrics, and then I've read a second paper which proved that the metric was not isotonicity, and it created stable loops. So the optimal local decision was to produce routing loops. So just ignore the problem. You can do this for some metrics, but not for all. So
no, isotonicity, as far as I'm aware, does not create persistent routing loops. Persistent routing loops are created by monotonicity. So, surprisingly enough, when I write the formulae, you think, okay, monotonicity is obvious. it's never going to fail. No reasonable metric can possibly fail monotonicity. And the big, big surprise is that actually monotonicity fails for a lot of things that look reasonable. BGP people have a tendency to design routing policies. They don't speak in terms of metrics, they speak in terms of routing policies. And when you try to reverse engineer what they've done, so BGP people are extremely annoying. They have some intuition, they don't tell you what the intuition is, they convert the intuition into regular expressions, and then they give you the regular expressions, and you have to spend a few months reverse engineering what they did in order to find out what the metrics are. And they end up writing metrics that are not monotonic in some rare cases. And that will create persistent routing loops. What non-isotonicity might create is oscillation, persistent oscillation between two loops, or non-determinism, depending on the order in which the routers converge, choosing different routes. But you don't have persistent routing loops with non-isotonicity.
For the Z-3 option, if you take account of the channel of every output,
yes,
you can, for example, taking account the channel of an output that is very far from you, then if we use using your channel, it's not good to fail.
So the question is, here I've given two extreme cases. The no memory case, I only look at the first hop, and the infinite memory case, which is I look at all the hops in the root. And what you're saying is that you would like k hops of memory. Look at the following k hops, because faraway hops are not going to interfere. Yes, that's correct. That is actually what I'm doing. So I lied here. I said that I'm using infinite memory. I'm actually using 8 hops of memory. And once again, fine-tuning is finding the right value of 8. Okay, and plus there are features in BabelZ that allow you to declare an interface as being far away. So if you have a tunnel, you can say, look, when you cross this tunnel, forget all the information, because the guys on the other side of the tunnel cannot possibly interfere with the guys on this side of the tunnel. But that is something that you have to configure manually, and I'm trying to avoid as much as possible manual configuration and have it all happen, do the right thing automatically. Okay, we're finding it difficult enough to make mesh networks in our environment. If we hope one day to have normal people use our software, we need everything to happen automatically. So that is something I'm feeling a little bit less confident about. Does that answer your question? Yeah. Yeah.
I'm not so sure if I agree about local and global optimums in the problem. I think that the point you are making is that you already defined the model of what you count for optimal, and because of that it becomes suboptimal when you have problems of non-isotonic metrics. Because this local solution you are getting, okay, at the end with BabelZ, is the global solution of the Babel without Z.
Yes, absolutely.
So this suboptimal solution is in fact something you called before an optimal solution in Babel.
Absolutely.
So the reason is maybe why we have that isotonic is because we have a stupid matrix which doesn't take into account everything which is happening in the mesh, and because of that we can say, okay, we have optimum, but this optimum works same in the practice. It's the same thing as local optimum we get later on. So from the point of view, what I'm thinking is that we are saying, okay, great, we got matrix with isotonics, we won't have any, we will get global optimum, but this local optimum is just a bad one.
Yes.
Not the
So if I understand Mito's objection, what he's saying is that what you are calling a non-global optimum is actually better than the global optimum you were getting for your previous, in some intuitive sense. Now, I'm speaking here in very clear terms. I'm assuming the metric is given, and I'm working on the routing algorithm. I'm not working on actually the network. Now, the job of the routing algorithm is to find the shortest path according to that metric. So in this case, in the easy case of the isotonic metric, the algorithm was successful. It was finding the smallest metric. Now in this case, we are getting a situation in which the routing algorithm is not doing its job. You're saying that's still better because the metric is doing a better job, so it more than compensates on for the failure of the algorithm, but it's still a failure from the point of view of the algorithm.
It's not doing it is not doing the better job. It is only doing the same job as before. That's the point. That if you that it is in fact the same thing as before. So if you cannot agree on BabelZ, if you cannot select the route, proper route, you are in fact doing the same thing of like what Babel without Z would do.
Yeah.
So in fact you are just degrade yourself to Babel.
You are right. So that is something that I've been unable to prove yet, because proofs when you are dealing with multiple metrics become extremely messy. It's very difficult to get your hand around reasoning with multiple different metrics. But I believe that the property you're claiming is true. That is that the routes chosen for the better metric are never worse than the routes chosen for the isotonic metric.
So, and the problem you have here is that you're mixing towards optimum.
Yes.
Where they are in fact two different things. So you have optimum 1 and optimum 2, or optimum 1 and optimum prime.
The optimum is defined very well. Optimum is shortest metric.
Yeah, of course, but in the sense of performance of the network.
Yes, absolutely.
You would say that you have two things, and you have like global, where to which you tend, and local, and in fact what I'm suggesting is probably this local optimum prime is the same as global optimum without prime.
So would you agree with the following formulation, that we have sacrificed a theoretical property in exchange for a practical property, and that's a deal that you're willing to make?
No, I'm saying that you just redefine the names, and because you redefine the names, you got now something which is not theoretically optimal anymore. But because
well, you do.
Okay, but I agree. But I understand that your definition of optimum is somehow based on the metrics, and it is. But from the point of view of how the packets are going through the network,
it is still better. I agree.
It is the way of how you are going in the local optimum of BabelZ is the same as how they are going in the global optimum of Babel.
Okay, fair enough. Fair enough.
And what I would like to add, maybe to connect my yesterday talks, is that what I was saying yesterday is that because we are using shortest path, we cannot have global optimums for complex metrics, because the shortest path algorithm itself. Okay, but now I'm again mixing global optimum with my sense of good routing and your sense of
minimizing the metric.
But I'm saying that in my sense of global good routing, the shortest path algorithms cannot make global decisions.
Okay. Yeah. Well, thank you very much for your attention.
If you want, you can send me your slides and I will upload them.